Good morning. Today we have section 9.8, and with this section what we want to do is we want to write a power series. So with the series you're creating that summation notation. A quick example just to have an idea of what we're going to try to do is we want to write e to the x, which as a polynomial we were able to write it as 1 plus x plus obviously x squared divided by 2 factorial plus x cubed divided by 3 factorial. We want to write this as a series, so the ... as it goes on forever, we can write this function e to the x, which is approximately this polynomial, to write it as a series. So to start, when we write it as a series, we need our summation, and usually we're going to use n. So n is equal to either 0 or 1. So it kind of depends on the situation where you're going to start, and then obviously with the ... we're going to infinity here. Well, as we look and write this as a series, it's really nice sometimes when you leave it what we did in section 7 instead of always simplifying. Sometimes it's good to simplify, sometimes it's good not to simplify, but to see where things come from. And so here obviously when you have it squared and 2 factorial and cubed and 3 factorial, that's really nice, and like this is 1 divided by 1 factorial. So we can see the general pattern here where we would have x to the power of n, and then in the denominator it would be n factorial. So for this particular situation, I'd have to end up starting with the 0 for my starting point. X to the power of 0 is 1. Remember 0 factorial is also 1. That would give us our first term. Then when we plug in a 1, obviously it would get this second term. When you plug in a 2, your third term, etc. So this is our goal today, is we're going to write power series. And we're going to look at power series and figure out where they converge and where they diverge, but really where they converge is what we're really going to strive to find, because they won't converge at all points. So when we look at our power series, we have two situations. We have our power series if it's centered at 0 and x is a variable, compared to if it's centered at c, and then here again x is our variable on this. But you can obviously see the difference, and that comes from what we did yesterday with our polynomials. If we have, if we're centered at c, we're going to end up with x minus c, that's to the power of n, and however it may look from there. But as long as you're centered at c, you better have that in there, that you are identifying that your center is c. And in this situation, obviously, we're not going to write in x minus 0. And so we can tell, okay, here we have our center now is 0. And that's what we have to find right away, is where is our centering point? What are we centered around? When we look at our polynomials or when we look at our power series. So number 4, for examples of power series. And all these are different, but they're great. They're power series, but we've been working on the entire chapter. If you're centered at 0, you're not going to see that with the x value. If you're centered at 1, you're going to have x minus 1, and you have to see that. When you write out all the terms, you would see that in every term. And if you're centered at a -1, obviously then this would be centered at -1. So that big thing, a key idea here, is that you have to figure out where are you centered. Moving on, just rather quickly to start here, the domain of our power series is we want to figure out, your domain is the values of x that make the series converge. So that's what your domain is going to be. We want our series to converge, and we have to find the specific numbers where they're going to converge. Every power series will converge at its center. So at least there's one point where every single power series will converge. Then we have 3 situations though. We can have a power series that converges only at its center. So if we think of the real number line, it will only converge at its centering point, nowhere else. So that's it. That's the only place that it converges. Or it can converge over an interval. And in this situation, there exists a real number r greater than 0, such that the series converges absolutely with that x minus c, that's representing your, like the center for it. is less than r, and it will diverge when the absolute value of x minus c is greater than r. And on here I said we'll talk about endpoints later. But basically that r, which I don't love that they made it a capital R, it does represent like your radius of this, and usually with radius we use a lowercase r, but for this particular section they always used a capital R. So here's our center, and then basically we're going to create an interval. So we have, we should probably write this as c minus r, and this would be c plus r, our radius, and then on our real number line we will converge over this entire interval. And endpoints, sometimes they converge on the endpoints and sometimes they diverge, and that's why we're going to talk about that later. We'll have to test every endpoint. So say, all right, at this endpoint, let's say our center, just for example, is 1, and let's say our radius is 5. Well, if your radius is 5, this would be -4, and this would be 6. We'd have to figure out, does -4 converge or diverge for this particular power series? And also we'll have to test, does 6 converge or diverge for this power series? But that's where you will converge over a given interval. And then the third situation is that your series can converge absolutely for every single value of x. And these actually end up being really nice, because here's your center. Well, they converge no matter what. It doesn't matter what number you plug in there. Great, it converges over the entire real number line. So if we go back and look at these three situations, and here if it only converges at our center, well then the radius is going to equal 0, because there is no radius to this. It converges at this one point and that's it. In this situation, the radius is going to equal a specific number. So we can say, all right, my radius, and radius is just like if you think about a circle. If my radius is 5, I can go 5 to the left, I can go 5 to the right. It's pretty basic. And in this situation, your radius is going to equal infinity. So basically everything works in that situation. And so we're going to be looking at these power series and figuring out when do they converge and when do they diverge. So for some examples, we want to find the radius of convergence, and it's really easy if we can use some of our specific tests from the first 6 sections. And so our ratio test is super easy to tell whether something converges or diverges, and our geometric series is really, really easy as well. And so those are nice tests that we can use. So for number 6, if we look at this situation, our power series from n equals 0 to infinity, and we have 2x to the power of n. Usually the first step that I say right away is to determine what is your center. Well, in this situation, we know that our center is going to equal 0 because we don't have x plus or minus a number. The next thing that we have to do is figure out what our radius is going to be. And in this situation, if we look at this, this is just a geometric series, which is really nice. So we know that a geometric series will converge if this portion is less than 1. So when we divide by 2, great, we can say that our radius is going to equal 1/2. Oh, and then if I go back to the directions, that's all it tells me to do, is to find the radius of convergence. Our radius is 1/2. Maybe we should go a little bit, we can be a little bit more specific here. And we can even go on for this one and find our entire interval of convergence. So there is a difference. Our radius of convergence is definitely just 1/2. Our center is just at 0. But if I ask you specifically now for our interval of convergence, we know in this situation, if you plugged in your 1/2 and our center is at 0, that means that we can go from -1/2 to a +1/2. Maybe not the best notation to start here. If you plug in a -1/2 into this situation, 2 times a -1/2 is going to give you -1. And with a geometric series, we know that it then, in that situation, it would diverge. So it would give you a parenthesis. If you plug in your 1/2, 2 times 1/2 obviously is 1. With a geometric series, we also know that, okay, well, my rate here is 1. It's not less than 1, so it's going to diverge there too. Yeah, maybe getting a little bit ahead of ourselves from what we actually have to do here. Moving on to the next one. X minus 1 to the power of n times 4 to the power of n divided by n times 5 to the power of n. So with this series, what I'm looking for right away is my center. And our center is equal to 1, given this situation. And then we also obviously have to find our radius. So in order to find our radius, this one is kind of an ugly looking series. And just to figure out, well, what test can we possibly use with this? And again, like I said, ratio test works for just about anything. And so if we use our ratio test, it's our limit, n is approaching infinity, and its absolute value. So the absolute value portion of this is really nice because that eliminates the x minus 1 to the power of n, and we don't really have to deal with it right now. So then applying my ratio test, the next it would be 4 to the power of n times 4 divided by n plus 1 times 5 to the power of n times 5. And then instead of dividing by our original, we're going to multiply by the reciprocal, n to the power of 5, or n times 5 to the power of n divided by 4 to the power of n. Simplify things out. 4 to the nth simplifies out, 5 to the nth simplifies out, and we are left with the limit n is approaching infinity. In the numerator we have 4n, and in the denominator we would have 5 times n plus 1. Well, this limit, the degree of the numerator and the degree of the denominator is the same, so we know this limit is equal to 4/5. Well, 4/5 is less than 1, and therefore this is going to converge, meaning this converges all the time. So if this converges all the time, your radius is going to equal infinity. So because no matter what I plug in here, I'm going to get that I'm going to get it to converge. It doesn't matter what x value I plug in. So then it's really easy if you want to create your interval of convergence. It's obviously would be from negative infinity to a positive infinity if it specifically asks for interval. But I'm just looking for us to find the radius right now. Alright, so now to talk about the endpoint convergence. If your radius is equal to 0, your power series will only converge at its center. You don't have a radius, you have no endpoints to check. Which is actually really nice, and when you get to these problems, it's like, oh, that's awesome. Same thing as if your radius is equal to infinity. So here's my number line, here's my center, but my radius is infinity. That means it converges all the time, and we don't have to check endpoints again. So we can write in here no endpoints to check. But keep in mind your interval of convergence, so that all the numbers, if we think about every number on the real number line, so interval of convergence would be from negative infinity to infinity. So this is definitely an interval, where here you can't even create an interval. It only converges at one specific point, and that would be our center. And if your radius is equal to a specific number, then you need to check both endpoints for convergence or divergence. And basically then you have 4 different things that could possibly happen. Because if you have one endpoint, so here's my center minus the radius, over here would be the center plus the radius. These endpoints, like if this one on the left converges, it doesn't mean the right one is going to converge. Or if the left diverges, it doesn't mean the right's going to diverge. So you have to check those two things separately. And so 4 situations, because this could converge or diverge, this could converge or diverge. So let's write in here that endpoints may converge or diverge. You need to test both of them. If it is going to converge, that means that that point is included, and it better have a bracket. So either bracket, either way. If it diverges, if it's going to diverge, that means that that point is not included. Those would be parentheses. But again, you can have the combination. So you can have the left side can converge, the right side may diverge. So you have to test both of them. It doesn't mean that they're not going to be the same. All right, so we want to find our intervals of convergence, and we'll start off with a pretty easy situation here. Our power series is from 0 to infinity, and we have x divided by 5 to the power of n. I always want you to find this center first, so your center is equal to 0. And this is a pretty easy situation because we know that this is geometric. So again, for geometric, as long as that ratio, that rate, x divided by 5, if that's less than 1, we know that it's going to converge. Therefore, x has to be less than 5. Solving for that, our radius has to equal 5. And we know that looking at this is pretty obvious. Sometimes after I write, here's my center, here's my radius. So my center is at 0, my radius is 5. Okay, well then set up your interval right away. So it's -5 to 5 would be our entire interval. We have to check the endpoints, and you have to show work for it. So the first one I always say, well, let's say what happens if x is a -5. Then you have your summation from 0 to infinity, and if x is -5, that would create a -1 to the power of n. You have to tell me the test that you're using. This is geometric. We know that our ratio, or our rate, is -1. Therefore, at -5, it will diverge. So if it diverges, we can put a parenthesis. You have to show me the work for both of them. So if x is equal to a +5, summation from 0 to infinity, you're plugging 5 in place of x. 5 divided by 5 is obviously 1 to the power of n. Again, this is geometric. Very rarely are they going to be the same. This is a pretty easy problem. And then we have our ratio is equal to 1, therefore it will diverge. I am expecting that you show all of this work. You cannot take shortcuts with this. Put a parenthesis there, and this is our final answer. Because we want to find the intervals of convergence. This specific power series will converge whenever x is from -5 to 5. The endpoints are not included. And that's a pretty easy one where you could look at it and obviously say it because it's geometric, but they're going to get a lot harder. And I want you to know what I'm expecting for work. So the first thing that I would do here is, number 1, figure out what your center is. Number 2, figure out what your radius is. And radius ratio test works really well for doing that. Then you can set up your interval. After you've set up your interval, you have to check your endpoints. So check when x is -5, check when x is a +5. Alright, so let's try a little bit harder situation. Number 16, our power series from n equals 0 to infinity, we have 3x to the power of n divided by 2n factorial. Again, first thing that you have to figure out is what your center is at. Well, I don't have x plus or minus a number, so I know that my center is just at 0. The next thing is you want to figure out what your radius is. Well, this radius is a lot harder than the previous one because it's not geometric. So in order to calculate or figure out our radius, really the ratio test is the easiest thing to do. So for radius, I'm going to be using the ratio test. Therefore, make sure that you have your limit. N is approaching infinity. It is absolute value. Then we'd have 3x to the power of n plus 1, which I'm going to write that as 3x to the power of n, times 3x divided by, this has to be 2 times n plus 1 and then factorial. So that really is like this, which gives us 2n plus 2 factorial, but the previous term, remember, is just the 2n factorial, and that's where those get a little bit goofy with the ratio test. So it's not just 2n minus 1. This, when I say an n plus 1, here's my n plus 1, that was the previous term. And then there's your factorial. Instead of dividing, we're going to multiply by the reciprocal of our original, which gives us 2n factorial divided by 3x to the power of n. Simplify, 2n factorial, simplify out. 3x to the power of n, those simplify out. And now I have the limit, n is approaching infinity, and we have 3x divided by 2n plus 2. We know that this ratio, if it's going to converge, this thing has to be less than 1. Well, in this situation, x is always a number. So x is some specific number here, and then as you plug in infinity, you have 2 times infinity, obviously infinity plus 2, which is infinity. So this side is actually equal to 0. So remember, x is a number, n is approaching infinity. X is a specific number. Any number divided by infinity will always equal 0. Well, then we get to this, which is kind of a weird situation. And is this true? Yeah, 0 is always going to be less than 1. Therefore, what this tells us is that your radius is equal to infinity. It works no matter what in every situation. So our radius is equal to infinity. That ends up being a really nice problem. So as long as your radius is infinity, your interval of convergence is negative infinity to a positive infinity. And the nice thing, you don't have to check endpoints. But make sure that you understand this thing, that x is a number. Any number, even if it's a billion, divided by infinity is still equivalent to 0. Because this ratio is always true, or this inequality is always true, then your radius is equal to infinity. All right. Number 24. Summation from n equals 1 to infinity. We have negative 1 to the power of n plus 1 times x minus 2 to the power of n divided by n times 2 to the power of n. Again, right away, identify what is your center. Well, in this situation, our center is equal to 2. Next, we want to calculate, well, what is our radius? In order to calculate our radius, we want to use our ratio test. So radius, our ratio test works really nice for all these ugly, messy things. And ratio test, it's our limit, n is approaching infinity. The really nice thing is it's absolute value. So because it's absolute value, we don't have to worry about this right now. I don't want you to cross it off and say it's not part of the power series, because it definitely is, but it's not going to be affected when you apply your ratio test. So then we have x minus 2 to the power of n times x minus 2, so it'll give us our n plus 1, divided by n plus 1, and then it has to be 2 to the power of n plus 1, which is 2 to the power of n times 2. Multiply by the reciprocal, n to the power of 2, or I'm sorry, n times 2 to the power of n, divided by x minus 2 to the power of n. Alright, so that simplifies out, that simplifies out, that simplifies out, that simplifies out. And we have the limit, n is approaching infinity. We are left with n times x minus 2 divided by 2 times n plus 1. This is a pretty realistic situation of what we're going to have. We know that for a ratio test to converge, it has to be less than 1. X is always a number. So if you look at in this situation, x is a number, minus 2, great, we have some number here, times n, divided by 2n plus 1. The other thing that I haven't emphasized very much yet is that x minus 2 is going to create some coefficient, it's going to be a number. but you can never ever break up your center. And why you can't is if you go back to our actual theorem, way back on the first page here, when it talks about convergence over an interval, it says that x minus c has to be less than your radius. So you always have to keep this situation. You cannot split up your x minus c, which is your center. Obviously it says there's your center as well, but you cannot break it up. So as we go back and look at this problem now, and okay, I know that this is a number, so my leading coefficient in this situation is x minus 2. Well, and why I'm doing that is because this is to n to the power of 1, this would be n to the power of 1. We know that they have the same degree. The leading coefficient is 2. This has to be less than 1 in order for it to converge. Well, then I would have x minus 2 has to be less than 2. You cannot break up that center. So if you want to keep it in parentheses or absolute value or whatever it takes, you cannot break it up. So this center has to be less than 2, which tells us that our radius is equal to 2. So keep in mind, and I don't know if I've said it enough here, I hope that I have, you cannot break up that center. It has to stay x plus or minus a number. So then we have a radius of 2. If our center is 2 and our radius is 2, well, now we can go back and we can say, well, what is our interval? Well, if my center is 2, my radius is 2, it'd be, my interval would be from 0 to 4. Now what we have to do is check our endpoints. So we have to determine, does 0 converge or diverge? Does 4 converge or diverge? So we have to go back and say, well, what happens if x is 0? Then what's going to happen? So if x is 0, we have our summation 1 to infinity. We have negative 1 to the power of n plus 1. And if you plug in a 0 in this situation, you have negative 2 to the power of n, divided by n times 2 to the nth. We want to simplify out as much as we can, and right now these can't just simplify out. So I have my summation. It's negative 1 to the power of n plus 1. I can factor out a negative 1 to the power of n times 2 to the power of n, because both, basically that's negative 1 times 2, divided by n times 2 to the nth. Well, now what happens is obviously those two things simplify out, and I can put together these two things. So if you have a common base, which we do, then we can add our exponents. So n plus n will give me 2n plus 1, all divided by n. Although this is a negative 1 to the power of 2n plus 1, it does not guarantee that this is going to be an alternating series. And so this particular thing, we started at 1 to infinity. If you plug in a 1, 2 times 1 is obviously 2, plus 1 will give you 3. Well, because you're multiplying by 2 every single time, multiplying by 2 will guarantee that it's going to be even. Then when you add 1, you're going to guarantee that it's going to be an odd number. So negative 1 will always be to an odd number. Therefore, this is always going to equal negative 1, and that's divided by n. Why I'm saying this is that you cannot use an alternating series in order to determine whether this converges or diverges, because it's not an alternating series. So you have to check those carefully. The nice thing is, though, we can look at this and just say, well, obviously this is p series. Our power, yeah, we should write down that we're using the p series. You have to tell me what test you're using. So simplify your summation as much as you can. So here it is, obviously simplified. Now looking at it, I have the p series. The power is equal to 1. Therefore, it's going to diverge. So when x is 0, it's going to diverge. We get to test what happens if x is equal to 4. So we have our summation from 0 to infinity. We keep the negative 1 to the power of n plus 1. If x is 4, plug it in. 4 minus 2 is 2. We have 2 to the power of n. Divided by n times 2 to the power of n. Those things nicely simplify out, leaving us with the summation from 1 to infinity, negative 1 to the power of n plus 1 divided by n. And now we can say this is definitely an alternating series. You know, like where here I had to put them together because it changed it. This is definitely an alternating series. We have to prove or show two things. Number one is the limit as n approaches infinity, its absolute value, so 1 divided by n. Is that equal to 0? Yeah, absolutely it is. Number two is it decreasing? So is 1 divided by n plus 1 less than 1 divided by n? Yeah, that's true. Therefore, this converges. You are expected to show this much work. You are expected to say what test you're using. You are expected to go through this and write everything out. I know that it is very tedious. They're going to be long problems, but those things are expected of you. If you don't tell me the test, you will not get all the points. Even if you have the right answer, you have to tell me what test you're using for this. And obviously then here, this one converges, so I put the bracket over here.